All right, good morning, everyone. We are now recording. Uh, I'm just going to make a quick comment. Actually, I should have made this comment before, but based on our chats just a few seconds ago, um, I wanted to point out that if you are, if you have a Rubik's Cube and you're playing around with it, which you're highly encouraged to do, you may not be at the stage where you know how to solve the cube. I'm just trying to bring up the course website. I didn't prime it in advance. Here we are. You may not be at the stage where you know how to solve the cube already. And you may be thinking, oh, come on, just get on with the course. I want to know how to solve it. Let's get to that material. Well, that's going to take us a little bit to get to it. And the reason is we want to get to a stage in the material where not only are we developing a technique for solving the cube, we are developing a technique that's based on the theory that we've uncovered. And so we are going to be strategic in how we solve the cube. But I appreciate that as you're playing with it, you might just want to know how to solve it. And so you may Google how to solve the cube. There's thousands of videos will pop up, all different methods. So I do have your back on that one. Let me just indicate that if you go to the Rubik's Cube part of our course and scroll down, there is Solve the Cube. So if you click on that link, it gets you to the basic 5-step solution of the Rubik's Cube. This isn't going to win you any speed competitions, but this is based on the theory that we will be developing. So if you just want to jump right to how do I move pieces around, there's basically only 4 moves you need to know how to do on the cube. And that is how to move the corner pieces around 3 at a time, how to twist 2 corner pieces in opposite directions. So they stay in the same location, they just rotate. And similarly for the edges, how to cycle 3 edge pieces and how to flip them in pairs. And then there's some moves written down there. We'll get into all of this. But as I said, if you just want to get to the heart of it, there's all the videos laid out here step by step on how to solve it. And so if you've got some downtime and you just want to get ahead and see how we are going to solve the cube, you are certainly welcome to jump through and go through steps 1 through 5 and see our technique and how we're going to do it. So that's just if you're really itching to get to solve the cube. One other thing is there are apps out there, mobile apps. You can probably find them on Android's store or the iOS store, which will allow you to hold up your cube to a camera and have it basically map where the colors are, the stickers are, and then you hit solve and it'll give you a sequence of steps to solve it. So if you really do mess it up and you just can't get it back to a solved state, with the face-to-face version of the class, people would pop by my office and I'd restore it for them as they were learning. But that's not going to happen now, so you can certainly find mobile applications that you can take photos of or at least take a camera and take pictures of the sides, and it'll tell you the sequence to solve. Yeah, yeah, exactly. It's been messed up for weeks. So those five steps in those videos will certainly help you get that sorted as well. And the benefit is it's getting you to familiar with the techniques that we're going to be used to solve the cube in this course and understand it from a theoretical standpoint. I chose those 4 moves because they're the only 4 moves you need to know how to do, and we will strategically build them in such a way that every move that's done, every twist of every face makes complete sense as to why we're doing it. And if you want to modify it, you'll know enough that you can modify those move sequences and make them your own. So it's, again, not about memorization. It's about total and complete understanding of why we do each move on the cube that we're doing it. Whereas if you watch some videos about speed solving and whatnot, it's just a list of moves that you're going to have to memorize because in some sense they're not quite clear as to why each move is being done when it's being done. So we're on a trade-off here. We're going to go for understanding over speed. And that's our goal over this course. Okay, enough about that. Let's get into the topic that we left off with last day. And this is permutations, and in particular, I've got to clear that out. there we go. Now that thing's not on the screen. And in particular, order. So we just finished off on the order of a permutation. And this is the smallest number that if you take the permutation and multiply it to itself that many times, you're going to get to the identity. Good question. Wouldn't speed, so in the comments, wouldn't speed come with understanding? In a sense, yes. So speed will come with understanding, but then there's the question of when you get down to the last layer, we're going to treat the corners QBs and set them into their right spots, and ignoring the edges, and then do the same thing for the edges. So we're going to treat them sort of independently and deal with them on their own. Whereas some of the speed solving algorithms that are out there have you look at the last layer and say, okay, these corners need to get 3 cycled, these these 3 edges need to get 3 cycled, but I need to rotate these corners, and I also need to flip these edges. So for us, those would be 4 different moves. But as a speed solver, you will have memorized like 80 different move sequences, and you would go right to the one you would need to apply at that moment. And so, yes, in some sense, speed will come with understanding, but the speed solving records really come with memorization. Yeah, you're absolutely right. You're in the hundreds of algorithms which you got to need for speed solving. Okay. So the order of permutation is, as I said, the smallest number, which we're going to say kills the permutation. So how many times you have to repeat the permutation on itself before you get back to the solve state or the identity. We did some examples here. So we given a permutation alpha, and we applied it to itself 3 times and got the identity. So the order was equal to 3. Then we ask the question, must such a number exist? So must there be a number that kills a permutation? In other words, for any permutation, must there be some smallest value which, when you apply the permutation or multiply it to itself that many times, gets the identity? And the answer is yes. And that's because we're only dealing with a finite number of permutations. So if you keep multiplying the permutation to itself over and over and over and over again, you eventually have to repeat permutations because there's only finitely many. And once you repeat one, then you can show that you had to have attained the identity somewhere along the way. And that was our argument. And this question was actually asked in the chat before we even posed it in the lecture. And the question was, does that mean that on the Rubik's Cube, if you apply a sequence of moves, turn the right face, the up face, the left face, the right face again, the up face. So do some sequence of moves and then repeat that sequence again and again and again. If you start with the solve state and you do that repetitive move sequence over and over again, must you get back to the solve state? And the answer is yes, you must. And that was a discussion we had following an observation that someone had in the chat, which was wonderful. Just minutes before class started today, I just Googled order of moves in Rubik's Cube just to see what would come up. And there was a MathStack exchange post that said orders of moves on the Rubik's Cube. And this person says, playing with my Rubik's Cube, I was thinking of facts that are immediate to mathematicians but novel to others. Here's one. Given a Rubik's Cube in the solved state, any sequence of moves, if repeated long enough, will eventually return the cube back to its solved state. And so that's sort of in layman's terms, what can happen. But for us, we've now got this expressions in terms of what we call an order. And so then it goes on to say, to a mathematician, which is now all of us would read this as follows. The moves on a Rubik's Cube form a finite group. In other words, they're part of the symmetric group, and therefore elements have finite order. So finite group, in other words, the finite collection of permutations, and elements have finite order. So that was our observation at the finiteness here. And then this person goes on to say, okay, what would be the order of RU then? So they know that if you apply RU, so turn the right face, turn the up face, and you do it over and over and over again, you eventually have to get back to where you started from. they want to know what is the number of times you have to apply it. And then the subsequent question is, what is the greatest order of an element in the Rubik's Cube group? Atomic move, yeah. So the as soon as I read your post there, atomic move, I thought of this thing just exploding. And so an atomic move is when you smash it against the wall because you're just so frustrated. No, that's not an atomic move. An atomic move is an atom. And so the building blocks. And so the building blocks are a quarter twist of a face. So the atomic moves are like a quarter twist of the right face, or a quarter twist of the right face in the clockwise direction, or in the counterclockwise direction. Those are what they meant by atomic moves. And so this person says, I tried repeating RU for a long while and lost count, but it did eventually return home. They just didn't know how many times. And so that's really what we're going to be interested in is, for a given move, how do we find the order? And we will see how to find the order of RU later today. In fact, what's interesting down here is, so there was this other question that said, secondly, what's the greatest order of an element in the Rubik's Cube group? So in other words, you got these move sequences on the cube. If you do a move sequence, then let's call that an element of the Rubik's Cube group, so a permutation. And if we repeat that move sequence over and over again, it'll eventually return home. What is the biggest order that a move sequence, for a move sequence on the Rubik's Cube? So we'll see that RU turns out to have order 105. You have to do it 105 times. Can we find a move sequence that has order 200? Can we find a move sequence that has order 1000? What's the biggest order there is for a particular move sequence? Yep, there is a straightforward way to find the order other than just keep doing it. And that's what we're going to cover today. So good question. Yeah, if it was just to keep doing it, that would get very tedious. So we're going to come up with a very quick way to find the order, but it has to do with how we represent permutations. And so we're going to have to slightly alter our representation and come up with a better one. So you can see here that someone says the order of RU is 105 by actual manipulation. Someone down here says, oh, there's something about 15s and 7 being factors of something, and you can get 105 that way. That's the way we're going to do it later today, so we'll see that. But this is what I wanted to bring your attention to. So for some time ago, I wrote my bachelor, not me, this person who's posting, wrote his bachelor thesis about element of greatest order. And then there's a link. And then they actually came up with a new theorem, etc. And the link points to this paper, which it's 11 years old now. So I read it in about 2011 when they first posted it, and it's a really nice exposition of the Rubik's Cube. These were all undergraduate students at the time in their final year, and they broke it up, and each one of them wrote a different part of it. And so if one of you or a group of you, again, for a final project, if you're interested in exploring some more things about the Rubik's Cube, there's some great stuff in here. And one of the chapters is an element of greatest order. So here they show that there is a greatest order for an element of the Rubik's Cube. It's 1,260, and they show how to find such an element. So there's a lot of good stuff in here. So I just wanted to point some of this stuff out, that as you're Googling around, not only do you find stuff related to the Rubik's Cube, but you'll find mathematicians like us who have treated it from a mathematical viewpoint, and there's some rich stuff out there as well. Okay, so let's get into some more stuff on order, and then we'll get into this new way of representing permutations. So that was our theorem 3.8.1 that said every permutation has an order, a smallest element that kills it, or a smallest element that turns it into the identity. What can we do with that? Well, here's an example. Suppose you know alpha has order 7. Then we could ask questions like, what is alpha to the 35? So we know that alpha has order 7. So that means we know that alpha to the 7 is the identity. So let's just write that down. Order of alpha equals 7. That means that alpha to the 7 is the identity. What is alpha to the 35? Any ideas? Just the identity. Yeah, exactly. So that's alpha to the 7 raised to the power of 5. In other words, if I multiply alpha to itself 35 times, that's like multiplying alpha to itself 7 times, and then doing that new element multiplied to itself 5 more times. This is the identity raised to the 5th power, which is just the identity. So then I could say, a follow-up. Those should be two different words. Follow up. I could say, what's alpha to the 37? Well, what's alpha to the 37? What would it be the same as? Any ideas? Yeah, alpha squared, exactly. We could say that that's alpha to the 35 times alpha squared, but alpha to the 35 is the identity, so this just results in alpha squared. Where did that square come from? I mean, we see where it came from the calculation we just did, but this is the remainder of 37 when divided by 7. In other words, we have that 37 is congruent to 2 mod 7. And so we can see that doing the calculation of alpha to the 37, we could simplify it and just do the calculation of alpha squared and get the same result. And that's because the order of alpha is 7. So anytime I raise it to the power of 7, it just turns into the identity. So this is where our congruences are going to come in. This is why I wanted to talk about number theory early on and divisibility and whatnot, because it's going to come in terms of these orders and raising things to various powers. Let's have a look at the next one. Beta is given by that permutation, 1 to 2, 2 to 3, 3 to 1. Does beta to the 62 equal the identity? Does beta to the 62 equal the identity? Yeah, no. What is it in terms of power of beta? What would it be equal to? Yeah, it's equal to the square. And so the idea here is that we first notice beta has order 3. Okay, why do we know that? I find it easier in terms of a picture until we introduce the new notation, which we're going to introduce very shortly. In terms of a picture, beta is this. 1 goes to 2, 2 goes to 3, 3 goes to 1. So in order for all numbers to go back to where they started from, we'd have to apply beta to itself 3 times. So that means that beta cubed is equal to the identity. And so beta to the 62 is equal to beta to the 60 times beta squared. But beta to the 60 is beta cubed raised to the power of 20 times beta squared, which is the identity raised to the power of 20 times beta squared, which is beta squared. Okay, I'm fine if you don't fill in all those details and you just go from beta to the 62 to beta squared and skip all of those in-between steps. But I just wanted to show you that we are using algebra here. We are using the fact that we're able to split up products and group products accordingly, which is convenient here as powers of 3 and whatnot. Maybe this last step, I could say, well, beta squared, but that's just beta inverse. Beta inverse. Why is beta squared the same as beta inverse? Well, because beta squared times beta is the identity. Beta squared times beta is the identity. So that implies beta squared is the inverse of beta. So that's just a quick observation. So we're tying inverses in here as well and just seeing how these things all relate. The last result, which is a theorem, says that if alpha is a permutation, if alpha raised to the power m is the identity, then the only way that could happen is if the order of alpha divides m. So another way to say this is the only powers that kill alpha are multiples of its order. Right, so above, alpha had order 7. So the only powers that would kill alpha would be 7, 14, 21, 28, the multiples of 7. If I had a number like 25 and I took alpha to the power of 25, it won't be the identity. What power would it be? Well, we could do the whole remainder thing. 25 has a remainder of 4 when divided by 7, so alpha to the 25 would be equal to alpha to the 4. So we can also find out what the smallest power is that's equivalent to that expression. We will prove this. We'll prove this in lecture or chapter, maybe I should say, the next chapter, which we will get to, chapter 4. We're just gonna delay the proof of this, but we essentially have all the ingredients here. I'm just delaying the proof because I want to talk about cycle form, and then we can talk about the proof of this. And it gives us a chance to revisit this thing. So it's always good to see something and then see it again to really get it settled home. Okay, so let's go and find this new notation. So this notation that I want to introduce, it's known as cycle notation. It's our powerhouse of notation. It's notation that we're going to use from this point forward representing permutations because there's so many benefits for it. It allows us to see the whole structure of the permutation just in one simple form. And so what is cycle notation? Well, I've drawn the arrow diagram on the left for this particular permutation. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 to 5, 5 to 1. But that arrow diagram, there's a lot of redundancy in that picture. And I can sort of simplify it down in some sense. Right? I don't need to write down 2 copies of 1s because a permutation is a function that goes from the set back to itself. So maybe I can build that into my diagram. So what I've done in the diagram over on the right is I said, okay, let's start with the number 1 as an input. What does alpha do to it? Alpha maps it to, or takes it to, the number 2. So I'll draw that in. There's number 2. And then alpha takes 2 and maps it to 3. So all I'm doing is just representing in this diagram what goes to what. And then 3 goes to 4 under alpha. 4 goes to 5. 5 goes to 1. So I might as well just reuse that same 1 that I had already drawn as an input. Now I'm thinking of it as an output. And this diagram represents all of alpha. There's nothing missing from it. It tells us exactly which numbers get mapped to which ones. 4 goes to 5, 2 goes to 3. We can read that off. So it's a condensed form of the arrow diagram, and this is known as cycle arrow form. And here's the key next step is I don't even actually have to use the arrows. I can do much like I did with the arrow form and write down just the numbers in an array. But here, I will just write down the numbers, but I'll write them down without the arrows between them. So I will start at the number 1 and I'll write it down. And then I just continue writing the numbers to the right of it as to what happens with following the arrows. So 1 goes to 2. So 1 goes to 2. And then 2, alpha takes 2 to 3. So I'll write 3 to the right of 2. And then 3 goes to 4. So I'll write 4 to the right of 3. 4 goes to 5. So I'll write 5 to the right of 4. And then 5 goes to 1. So I'll just wrap it around and imagine that that last number I wrote down, it now goes back to 1. So then I've got this closing bracket that I'll just put in. So I've got opening and closing brackets. And that is our cycle form for the permutation. It doesn't force us to have to write a top row and a bottom row in the array form. It contains all the information we need right there. And so this represents the fact that each number maps 1 to the right and the last one maps back around to its start. The only problem with this notation, and it's not really a problem, it's just something to observe at the start, is that it's not unique. Right? I could have written this in, well, I could have started at, say, at the number 3 and said, okay, if I start at the number 3, 3 goes to 4. 4 goes to 5. I'm just looking at the cycle arrow form and just writing down the numbers as they come up. 5, where does it go to? It goes to 1, 1 goes to 2, 2 goes to 3, but that's the one I started with. So I could write this permutation in this form as well. Now it's really just the same as the one I wrote in green, except I've started here and just moved this way and then wrapped around and come back. So it's not really a problem in the sense that whatever number I start with is just going to be sort of a shifting of the numbers around. The order's not going to change. It's just how they shifted around. What I started with is going to be different. So we just make a convention. Our convention is that when I write down this cycle using this notation, I just make sure that the smallest number is at the start. And then that's going to specify uniqueness in its representation. So that's going to be our convention. So let's go ahead and look at another example. Let's write this beta in cycle form. So I'm going to draw a picture for beta first, but typically we won't use pictures, but I just want to do this for the first couple of examples just so we get a feel for what these things are. So here's my picture. I'm going to write down 1. 1 goes to 3. And then 3 goes to 6, and 6 goes to 1. So 1 goes to 3. And then 3 goes to 6. And then 6 goes to 1, so it comes back around to where we started. And so that's part of beta. It cycles these 3 numbers around. What else does it do? Well, it takes 2 and sends it to 7. And then 7, it sends to 4. And then 4, it sends to 8. And then 8, it sends to 2. So beta also cycles these 4 numbers around. Just looking at some of the comments. Is it sufficient to say that 62 is not divisible by 3? Yep, so 62 is not divisible by 3, therefore it's not going to reduce alpha to the identity. That's one way to do it. Alpha, order of alpha, and order of alpha to the k for k an integer. That's a good question. Are they the same? So good question, Eric. Is order the alpha and order the alpha to the k the same? And there's a comment by Brian, not necessarily. Yeah, so if alpha has order 6, then alpha squared would have order 3 because the square would have already partially killed some of alpha. And that's what we're going to see in these things here. So good questions. I like where that discussion's going. So I'm going to finish off this one and say 3's been used, 4's in our diagram, 5's not in our diagram, but it goes to itself. 6 is in our diagram. Yep. 7's in our diagram. Good. 8's in our diagram. So maybe I will write 5 in there just to sort of specify that 5 goes back to itself. So there's a picture representation of what beta is doing. And in terms of cycles, we can say, okay, what does beta do? Beta takes 1 to 3, 3 to 6, and 6 goes back around to 1, so we can put a closing parenthesis in there. Now, we're not using commas. So when we get into double-digit numbers, you just want to make sure you leave enough of a space between them so it's easier to read. And not using commas in cycle form is a common convention. So what about the next one? Well, 2 goes to 7, 7 goes to 4, 4 goes to 8, and 8 goes back to 2. And then we had 5 goes to 5. So there would be beta written in cycle form. And so to come back to the comments that you guys were having in the chat is, notice that if I was to take beta cubed, I was to take beta times beta times beta, notice that would wipe out that 3 cycle 1, 3, 6, because all those numbers would return to themselves. But the 4 cycle 2, 7, 4, 8, if I cube it, it's not going to get back to itself. It's actually going to turn into its inverse. And so beta cubed is going to turn out to be a 4 cycle. and that would have order 4, which is not the order of the original beta, which we still have to figure out what it is, but you might start to see now that the order of beta, we got to return all 3 numbers back to themselves in one cycle, but we also have to return all the 4 numbers back to themselves in the other cycle. And so it's going to have to be a multiple of 3 and a multiple of 4. So the smallest multiple of 3 and multiple of 4 is 12. So it looks like the order of beta is 12. So these are the kinds of things that we're going to be using. In fact, now I've just sort of answered the question about, are we going to be able to find orders without multiplying a number or permutation to itself that many times? And the answer is yes, it's going to be present to us in the cycle form. So that's what today's all about. So we will get this all straightened out and look at lots of examples. So cycle form is a compact way to represent a permutation. It still contains all the information and it reveals more structure about the permutation. So for example, additional structure I get from this cycle form is, what about this question? If I said, is there a power k such that if I took beta and raised it to the power of k, remember these are functions, right? Beta, beta squared, and that, these are functions, these are permutations, input, output, such that beta to the k of 1 is 4. So is there a way to power up beta so that you multiply beta to itself many times and get it so that when you put 1 into that thing, a 4 comes out? What are your thoughts? Yeah, no. And the reason it's no is because, let's look at where 1 is. When I apply beta once, it takes it to 3. When I apply beta again, it takes it to 6. When I apply beta again, it takes it back to 1. So beta to the 3 is 1. Beta to the 4 of 1 would get back to 3. Beta to the 5 of 1 would take it to 6, and so on. So we just keep cycling around. So the answer here is no. Beta to the power of k of 1 is either 1, 3, or 6. And that's it. And we see that from our cycle form here, is that 1's only allowed to be sent to 3 or 6 or back to itself 1 again. It's trapped in that cycle. Same with 2, 7, 4, and 8. They're cycling around each other. So 2 can go to 7, to 4, to 8, back to itself, but it can't go to any other numbers. So that's additional structure. That's what I meant about more structure we can see in this. Let's express the permutation in cycle form. So this is now gamma. So my goal is to, much like we did with beta, to do the same thing with gamma, but without having to draw the picture first. Oh, and I will add one more comment. I set it down here. Our convention is to leave off 1 cycles. So with our convention, we would typically just write this as 1, 3, 6, and 2, 7, 4, 8, and not bother writing down the 1 cycle 5. Our convention is that if a number is missing in the decomposition, then it must go back to itself. So that's another time saver. We don't have to write, in our array form, I had to write 5 up top and then 5 down below to say that 5 goes to 5. Here, in the cycle form, I just leave 5 off. And the convention is that if it's not there, it mapped to itself. It got sent to itself. It didn't move, in other words. So let's express gamma as a cycle. So the way we're going to do this is we are just going to go and pick the numbers in numerical order and see what happens. So I start with the number 1, and I just play the game of, what does gamma do to it? Well, gamma takes 1 and sends it to 4. And now what does gamma do to 4? It takes 4 and sends it to 2. And then what does gamma do to 2? And notice all I'm doing is I'm just going into the first row, finding the number I'm interested in, and seeing where it goes. So it takes 2 and sends it to 9. Where does it send 9? I look at the array form. 9 gets mapped to 1. Okay, so 9 goes back to the number I started with. So there's my first cycle. It's a 4 cycle. So it's just permuting 1, 4, 2, and 9 amongst themselves. What else is it doing? So I scan through that one and see which is the smallest number that's missing. 1, 2, 3 is missing. So I'll use 3 to start off my next cycle. 3 goes to 5, and 5 goes to 3. So I close it off. And how about my next one? So I've dealt with 1, 2, 3, 4, 5 are all done. They're all present in my cycle structure. 6 I still have to do. 6 goes to 7. 7 goes to 10. And 10 goes back to 6. So there's my next cycle. So that deals with 1, 2, 3, 4, 5, 6, 7, 8 is not done yet. So I look up and I see, oh, 8 goes to 8. So that's going to be a 1 cycle. I'll leave it off. 9 is already done. It's in my first cycle there. 10 is already done. So I've dealt with all the numbers, and there's my permutation in cycle form. And it tells me a lot of information. It tells me the 4 numbers, 1, 4, 2, and 9 are all being permuted amongst themselves. 3 and 5 are getting permuted amongst themselves, and 6, 7, and 10 are getting permuted amongst themselves. So let's have a look at the next example. Again, this is trying not to forget the fact that these permutations are functions. So we can act or do things with them like we would with functions. So what is the value that comes out if we put this value in? So there's alpha, and we want to know what alpha of 3 is. So I go up to my cycle form, and I find the 3, and the output when I put a 3 in is the number that sits to its right. So that would be 7. And then the next one is, what's alpha 9? Well, I find 9 in there, and I find the one to its right, but I use wraparound in case I'm at the far right. So if 9 goes in, 4 comes out. What about alpha squared of 1? So I find the 1, here it is, and I'm applying alpha twice, so I make 2 hops, and a 3 comes out. And what is alpha to the 8? Well, 8 is missing, so the assumption is that if 8 is missing, it's part of a 1 cycle, so it means it would have gotten mapped to itself. So from the cycle form, we can get things such as the values that come out for inputs, and even powers of values that come out for various inputs. The powers just means we hop along that many times. So very nice notation for finding powers and values. So let's look at products again. Now we're going to compute products. Instead of having to use array form or our arrow form, we're going to see how we can compute a product using the cycle forms. So if I take alpha, beta, what I do is I write down their cycles next to each other. And ultimately, our goal is to try to write this thing down using cycles that are all disjoint. So notice that in our examples above, like if I look up at gamma above, all those cycles are disjoint. 1, 4, 2, and 9 appear in the first cycle, but they don't appear in any of the other ones. This is known as disjoint cycle form. And the idea is that if I compute a product of various cycles, I can always write it in a disjoint cycle form just by figuring out what each of these numbers go to. So for this, I do the same thing I did before to find its disjoint cycle form. I write down the smallest number that I could consider as an input, and I figure out where does it go as an output. So I have to read along. I'm thinking of these as permutations that are being applied one after the other. So if I start with 1 going in, then 3 comes out. It goes into the next one, and it's like, oh, it's not present in there, so 3 still comes out because it didn't do anything to it. And then I go into the next one, 3 goes in, and 2 comes out. So I have that, and this is how I read it. I'm sort of reading these arrows. I say 1 goes in, 1 goes to 3. I look at the next permutation, the 1-4 cycle. 3 still goes to 3. Look at the next permutation. 3 goes to 2. So 1 ultimately goes to 2. And then we do the same thing with that 2 now. Now 2 is going in. And I just read across. For that first permutation, that first cycle, 2 goes to 2. The next one, 2 still goes to 2 because it's not moving it. And the last cycle, 2 goes to 5. So 5 comes out. And then the 5 goes in. The first cycle takes 5 to 7. And then the next 2 cycles don't have a 7 in them. So 7 just comes out. So 5 goes to 7. And then what does 7 do? 7 goes to 1 from the first permutation. And then you get into the second one, the second cycle. 1 goes to 4. And then 4 goes to 4 in the last one. So 7 goes to 4. And then where does 4 go to? 4 goes to 4 from the first one. 4 goes to 1 now in the second one, and 1 goes to 1. So 4 goes to 1, and we're closed off. So that's part of it. Now I still need to keep working. I've got 1, 2, 3's not in there, so I still need to figure out what happens with 3. So what does 3 do? The first cycle takes 3 to 5, and then the second cycle doesn't do anything, so 5 still's at 5, and then 5 goes to 3. So 3 goes to 3. And so that gives me 1, 2, 3, 4, 5. 6 isn't present anywhere. And I could put it in there as just a 6 goes to 6. And we got 7. So we got all the numbers now. They're all there. And so I can use my convention of leave off the 1 cycles, and that's our product. 1, 2, 5, 7, 4. So that's what we get by doing alpha followed by a beta. How do we get 1 goes to, so I didn't get 1 goes to 1. What I did get is, oh, I might have said it at some point along the line, 1 goes to 1, but it would have been, here. So let's say I'm trying to figure out where does 4 go to. So I'm at this point. I've got this 4, and I'm like, where does 4 go to? So I scan through the first permutation, and I get that 4 doesn't go to anything. 4 doesn't change, so 4 goes to 4. So then 4 comes into the next one. It's right here. It goes to 1. So now 1's coming out of that permutation. And then it goes into the next one, because the next one's going to tell me that if it changes 1 or not. But the next one only consists of 2, 5, and 3. So there's no 1 in it, so it's not going to change it. So that's where 1 goes to 1. So in the end, 4 ultimately goes to 1. Yeah, I'm reading left to right, exactly. Always reading left to right, moving across, and that was our convention. Maybe I should get left to right. So yeah, sorry, my camera's reversed. So we always start on the left and read across to the right, just following it along. Much like we did with our array forms of sticking them next to each other. It's just now I'm using the cycle form to read off the same information. Okay, properties of cycle form. Every permutation can be expressed as a product of disjoint cycles. So that means cycles that don't contain numbers in common. For example, alpha and beta, the very first thing I wrote down was a list of cycles that are not disjoint. Right? There was numbers that were in common. Like, for example, there was a 5 here and a 5 there. There was numbers that were in common. So every permutation, I can always write it in one that's in disjoint cycle form. So that one I reduced down to just a single 5 cycle. And the other thing to observe is that if you have disjoint cycles, that they commute. And so, for example, if I took alpha beta and I wrote down the product, that would be the product. If I wrote down beta alpha, that would be the product of beta alpha. And you may say, you didn't really do much. And the answer is, you're right. because they were disjoint. So this would be their cycle form. Both of these, however, if we were to write them in array form, they both represent the permutation. 1 goes to 3, 3 goes to 4, 4 goes to 1, and 2 went to 5, and 5 went to 2. So in some sense, what's happening here is this permutation is in some sense consisting of two kinds of chunks. The 1s, the 3s, and the 4s are getting mixed up, and the 5s and the 2s are getting mixed up, and that's in the array form. But we're seeing that directly in the cycle form. That's why the cycle form's a benefit, is it gives us structural information. It tells us which numbers are getting permuted amongst themselves. And notice it doesn't matter whether I wrote the 1, 3, 4 cycle before the 2, 5 cycle or after it, because it's just saying that the 1, 3, 4 are getting mixed up in that way and the 2, 5 is getting mixed up in another way. So they commute. I've indicated here it's sort of the shirts and socks analogy. So the idea is that I can put my shirt on and my socks on in either order, shirt first, socks second, or socks first, shirt second. The end result's the same. It's the socks and the shoes that cause a problem. Order matters there. I don't want my socks on top of my shoes. But the shirts and socks, they're disjoint. They have nothing to do with one another. So order doesn't matter. And that's the idea here with disjoint cycles. It doesn't matter which order I do them in because they're affecting different numbers. Okay. I want to just observe that if we have alpha and beta as defined above, what is beta alpha beta inverse? Sorry, beta alpha beta, not inverse, no inverses here. What is beta alpha beta? Now we could multiply these things out. I could write down beta, I could write down alpha, and I could write down beta again, and I will. But the observation is that we know that these are disjoint cycles, so they commute with each other. So I could write them in the opposite order and it wouldn't make a difference. We'd get the same result. And now I have a 2 cycle multiplied by another 2 cycle. So I have a permutation 2, 5. So switching 2, 5. And then the next permutation just switches them back. So these together multiply to give us the identity. That's why I've canceled them out. So this works out to be alpha in this case. So this is how we can use disjoint cycles commuting, is that we can do some algebra with them and we can spare ourselves some calculations. Notice I didn't do any calculation here. I just noticed that I could switch the order of 2 things and then had 2 things canceling. So we're starting to develop some notation and then some power for deciding whether we need to do computation or not. If alpha and beta commute, then we have that result, that alpha beta raised to the power of m is the same as alpha to the m beta to the m. And that's just because alpha beta to the m is equal to alpha beta, alpha beta, alpha beta, dot, 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 alpha beta. And we can take all of the alphas and push them across all of the betas because they commute. And that gives us alpha to the m, beta to the m. So the thing is that they need to commute in order to do this. We will raise powers of products, but the only way we can just individually distribute the power across the product is if we know they commute. All right, I will give you one last thing. We'll finish this lecture on next day, but I will give you one last thing regarding inverses, because I want to show you with cycle form how easy it is to compute an inverse now. So remember, the cycle form tells us that 1 goes to 4, and 4 goes to 7, and 7 goes to 3, and 3 goes to 2, and 2 goes back to 1. What the inverse is supposed to do is just reverse all those arrows. So to find the inverse, all I do is just reverse the list of numbers. 2, 3, 7, 4, 1. I just write it backwards. So reverse alpha. And we found the inverse. That's all we do is write it in reverse. Now, our convention is to usually start with the smallest number. So at this point, we can say, okay, I'll rewrite the cycle so that I start with the smallest number. And that's going to be 1. And then I just read from left to right, cycling around if necessary. So if I start with 1, the next number is 2, 3, 7, 4. And that's our inverse. Thank you. I forgot the inverse. Yeah, absolutely. Yeah, I forgot to write down the inverse sign on the alpha. So it should be alpha inverse. And so that tells us that we can write down the inverse very quickly. And in fact, you can see how I can go perhaps from the alpha to the last cycle I wrote down for alpha inverse, is that I just take the first number, because by convention it's already starting with the smallest number, and write that one first. And then I just reverse these numbers. Reverse the remaining ones. Read them backwards, 2, 3, 7, 4. And I got the inverse. And that's it. That's how we compute inverses. So we'll finish this up next day. I'll stop the recording now.